Hi, everyone. So nice to meet you. I'm Alessandro Luca, and today I will introduce you the webinar that are going to be the preparation for the BioHackathon for the BITS for this summer. Okay, I'm sharing the presentation. Perfect. So just as a short recap, the BioHackathon is going to happen shortly before the BITS on the 10th of June in Naples this year, it's going to last half a day, so it should be around from 2 until 6 p.m. This is the webinar schedule, so all the webinars are actually useful for arrived there already prepared with all the information that you might need in order to handle the biohackathon. Here in this QR code, you can connect to you can find the biohackathon website, so you can find all the other information that you need there. The first thing that I'm going to do, so today we are going to talk about reproducibility, containerization, and HPC, that is the high performance computing. Then we will introduce the single-cell RNA-seq, so the web club part, and then we will start with the last two sessions of single-cell RNA-seq, that is computational meat part 1 and part 2, for a last session, that is the Q&A plus spoilers. That is the spoiler session. So you will know a few things about what will be the biohackathon about. So let's start. Let me just check if there are any comments or anything. Not yet. Perfect. So let's start directly with the high performance computing. I will be very brief on this part, and then I will leave the stage to Giacomo. I will just give you an idea about what is the high performance computing. So it is not what you expected. It's like a supercomputer. It is at least not just that. But why do you need high performance computing? So basically, bioinformatics today is improving and is exploring new possibilities like AI, for example. And the data generated by the new sequencing technique are huge, like terabytes of data. So they are really big. Sometimes it's really difficult to handle all of them with, of course, with a laptop, but imagine also just with the server. If they are working several people all together, if the server is not well organized, well, there is going to be a problem. That's why high performance computing, it is important, because at some point we're arriving in an era in which bioinformatics is going to be the block point in which, so people will produce data. There are a lot of data out there, but the problem is that analyzing this data will take some time and will take resources. So using HPC is actually the best option we can have in order to better analyze this data with the limited amount of time. So the key component. So what is HPC? So generally speaking, an HPC is a series of components. Of course, you're going to have a CPU and a GPU for processing all the workloads, but also you're going to have you want to execute tasks simultaneously, and you can do that with two different ways. The first one is using multi-threading. So you can imagine, as your computer is handling different operation at the same time, you can do the same also with HPC. But also you can use a distributed computing. So you have a cluster. So you have multiple computers working together. And already you can imagine that setting up all of this, it will take some time. Of course, it is required a high-speed networking, a storage system with all the backup and everything you might need. But one thing that is super important is the job scheduling and resource management, because believe me, whenever you access to an HPC, unless you are super rich, you're not the only one accessing the HPC. So having a good job scheduling, is actually what makes the difference between an HPC that works pretty well and another one that doesn't. Here there are some common bioinformatic tools. So if you are not familiar with bioinformatics, here there are just listed a few bioinformatics tools that actually they are really demanding in computational resources. Some as Bowtie or BWA that they are required for aligning a human genome, actually also STAR, for example, but this is for RNA-seq. Also another one, it is AI ML for genomics. I mean, this tool is really important to search deep variant and deep genes. So you can see where we are going, right? Because having an HPC means that you can also use a GPU and some resources that you might not have on a normal computer. Also, in order to give each user a different workspace, the HPC is actually installed, set it up by environment through containerization and the package manager. Like, for example, Conda, Docker, Singularity. You will see today Singularity more in the detail, and you will see how to use it. But before to proceed to that part, just a few last words on HPC for AI, because what you will use, it is an HPC, but it is called HPC for AI, and is hosted, this HPC infrastructure at the University of Turin. So this infrastructure is out there since quite some years right now. So we have several projects opened. And if at some point after this biohackathon you want to use these resources, please just search on Google for HPC for AI, University of Turin, and you can request some rates for, I don't know, you want to use it for 1 week, 2 weeks. There is a coin system, token system, so you can just buy some token and use it. It is pretty simple to use it. And you can also request configuration like the one that we will show you and that you will use during the biohackathon. So yeah, during the biohackathon, you will be divided in groups. And for each group, we will provide a virtual machine. And each virtual machine has 16 CPU, 32 gigabytes of RAM, some storage space and fast RAM and so on. But basically, the most important thing that you might need to know is that you can access to this HPC through two software, RStudio or JupyterLab. And yeah, I'm going to show you directly what you will see that day. So this is the web page that you will see and that you will use to connect to the HPC. And you can choose between RStudio and JupyterLab. Basically, according if you want to use R or Python, or if you're more familiar with one or the other one, that's totally the same. So just clicking on RStudio, I'm already logged in. Of course, you will be requested for some credentials, but here is the standard interface of RStudio. As you can see here, we have the R terminal, the console from R, but also we have the terminal. I just want to take a few notes about Jupyter and RStudio because the environment is connected. As you can see, this one over here is the terminal of RStudio, and yeah, just the bash command works. And if I create a directory over here, mkdir temp, for example, and then let's go back. As you can see here, temp directory is created. One thing that I want to show you, just if you open JupyterLab, I mean, it's the same environment. As you can see here, you have all the folder. Here you have your terminal. If you press plus, you can open either a notebook or you can open the console. But basically, the terminal is one of the most important things because through the terminal, you can actually install other software, but you are going to run Singularity. That is what you will see later after this presentation. One thing that I wanted to show you is that, see the temp over here, this folder we created in RStudio, and we can see that here in the JupyterLab. So the two environments are actually connected. two environments from the same user, of course. So each of the user will have a different virtual machine. So the same environment shared between RStudio and Jupyter Lab. And yeah, I believe that's all from my part. Yeah, thank you for listening to me for this short introduction, and I will leave the stage to Giacomo.
Hello to everyone. So let me share my presentation to you. Okay, so again, good afternoon to everyone. My name is Giacomo Baruzzo. I'm assistant professor at the University of Padua, and today, together with Giulia Cesaro, a postdoctoral researcher in my research group, we're going to introduce you to the wide world of software containerization. And why we talk about software containerization? Well, because it's a very convenient solution to tackle several problems that you may need to handle when you develop or install scientific software, especially in the context of bioinformatics. So let's start from a practical scenario, what we're going to see today. We're going to introduce what is a container, why we talk about container, the idea behind software containerization and some definition, as well as some pros and cons. They're going to see container compared with other alternatives like virtual machine and virtual environment. And we are going to conclude this first part of the webinar listing mainly the main container engines, what they are, how they differ somehow, and what we need to take care of when we want to use containers in a remote server or in an HPC system as the one described before by Luke. So, why we talk about container? Well, in a typical scenario that many of us as bioinformaticians experience basically every day, very often we need to install or set up some analysis pipeline, some advanced software to do our research. Each time we need to install a software, we have some requirements to fulfill, meaning that to be able to install the pipeline that we want or the package that we need, whatever, we need to first fulfill some requirements. For example, we should have a specific version of Python or R installed in our system. Maybe we should have a compiler to compile part of the software, or have a specific library like here, TensorFlow, to let the application run properly. What's the point? Well, the point is that depending on which computing system we are using, our office PC, our laptop, or the cluster in our department, well, each of these computing systems have a different operating system. Here, for example, Fedora 24 for the office PC, Ubuntu 18 for the laptop, Red Hat 7 for the cluster. Each of them may have different version of the software compared to the one that we need. For example, here, Python 2.7, but we need Python 3.7. Or maybe some other software is not even installed, like here, TensorFlow. So the point is that each time we need to set up an execution environment to run our software, we need to first install all the dependencies and then install our software. And again, depending on which machine, we need to install different libraries of software or update to more new versions, some library or some programming language or whatever. And this is an effort that we need to do in each of these machines, again, to fulfill the requirements and to be able to then use and install our software. As you may have experienced, is sometimes quite time-consuming setting up the right environment for the required software in different computing systems. It may be hard to install some libraries, some packages, some dependencies, maybe because they include some complex compilation step, or it's quite hard to download the right version. Or maybe, like if you work on a remote server or in a HPC environment, well, sometimes you have not very often, you have not the administrator privileges, meaning that you cannot install all the software that you want. So even installing software can be time-consuming and challenging. And typically, this is a task that the user have to do by their own, with some skill, with some knowledge, with some time, or asking to some system administrator, especially, again, if they use remote server like the server that you may have in the lab or the cluster that you may have in your institution. And also, installing software can be difficult. Again, we already saw installing specific version of a library or doing some complex compilation step. And also, we pay attention that the software that we install hopefully would not broke other existing software. So maybe we update a library because it's needed by our new package, and this broke some compatibility with already installed software. So even installing software that is the basic step to do any computation could be challenging. Even worse scenario, maybe the application that we want to install or to update, well, is not fully supported by the specific operating system or by the computing art that we are using. So we have a problem in terms of portability, meaning that the software that we want to set up works only on some system, and maybe we are not lucky, we are not using one of that system. Or problem in terms of reproducibility. Maybe the application that you want to install, it behaves differently on different operating systems. Maybe, I don't know, in Ubuntu, the last available version is the 1.0 for that library. On Debian is the 1.1. So when we install the lowest available version in two different systems, you're really installing two different versions of the software. Or even more subtle, maybe the software that we install, we are able to install the same version on all the possible systems where we may need to install it. But this software has some external dependency. It relies on some external library, for example. And this external library may behave differently in different operating systems. So even in this case, we may have some problem in terms of reproducibility. So many things may go wrong, many bad things may happen each time we want to set up to install a software. Well, a possible solution to many of these issues is using container. So Italy would like that the software that we use is easy to install and also don't break any other existing software, is portable, so we have no issue that the software works only on some system and on another, and is reproducible, meaning that when I install a specific version of that software, I would like that the results that I obtain are reproducible, are the same across all the other operating system or other version of the operating system. So what would be a needed solution? Well, instead of installing each time the software, the required library and the dependencies, just install all the things that we need one time. Let's put the dependency, the libraries, the data, the wanted software, put everything and install everything in a box, such that when this box exists, I can just release it to the user, and all the users that use such box already found the software installed and they can just use it. Well, the good news is that such boxes exist and are called containers. So the idea behind container is that inside this box, there is a specific and immutable version of the software that we need, already installed. So it doesn't contain the instruction on how to install. It contains already the software installed and ready to be used, together with all the other things, data, libraries, dependencies, OS packages, all the other piece of data and software that are needed to run it properly, in a way that we can run it everywhere, in our PC, in your colleague's laptop, in a HPC cluster, on the cloud, whatever. And this is really one of the strengths of container, because thanks to this fact, we can achieve reproducibility, accessibility, and portability. The fact that inside a container there is a specific and immutable version of a software, meaning that even if we want, we cannot change the software inside the container, this is a guarantee for reproducibility. The fact that the software is already installed together with all the possible dependencies, well, this improves accessibility, because basically the user of a container really don't need to install the software. They can just run it because it's already installed within the container. And also, obviously, portability, because again, each person that have the container image we are going to learn in a few slides, can just run it, and inside the container we'll be able to use the computing environment present. So can just use, no install, the libraries, the software, whatever is present inside the container. In this first part of the webinar, we are going to see general concept of software containerization. We're going to learn a little bit better what it means, reproducibility, accessibility, and portability. While in the second part of the webinar, the one held by Giulia, we are going to learn really how to use and how to create container using a specific software called Singularity. But let's see in a practical way what it means using container. Let's say that you have your colleagues, James, that have his own PC in the lab where he have his favorite operating system, Ubuntu 20 plus, I don't know, Python 3.7, a version of TensorFlow, some file and folders, and a container engine, a software that can run container. Then another guy in the lab, Bob, is able to use a container to create and to release container. And Bob, in his container, it put his favorite operating system, Fedora 34, the version of Python and R that needed for his software, that is just maybe a Python script, plus some other test data. Bob packed everything, the operating system, the programming language, the script, the library, whatever, in a container. Then, when James ran Bob container in his PC, well, James' PC magically seems to be as it works on Bob container. So when James ran a container provided by Bob, then on James' PC, now Fedora 34 is available. Python 3.6 and R 3.2.5 are present, already installed, they can just use it, plus all the data and the script, the file that Bob put in the container are now available even to James. Plus, James has also the possibility to access to other file and folder present in his PC. This means that if Bob gives his container to another member of the lab, maybe Susan, that is using a laptop with a different operating system, other software installed, other file and folder present, where Susan ran Bob's container, even Susan's laptop now is able to use Fedora 34, the version of Python and R put in Bob container, access to the file and folder present within Bob container, plus again, the possibility to be able to read and write on other file and folder present in Susan's laptop, maybe where there are the data that Susan wants to process using the computing environment set up by Bob. So this is really the power of container, that we can define in a more formal way as a way to encapsulate an entire execution environment, meaning the software that we want, all the dependency, the libraries, the package of operating system, the environmental variable, the runtime code, the data, whatever we need can be encapsulated inside a container, and this container can run everywhere. On James' workstation, on Susan's laptop, in your department cluster, or in the cloud, whatever. You see here, anywhere. Well, really, there are just 3 requirements that a machine should fulfill to be able to run such container. First, the destination machine, the target machine, should have installed a container engine. Well, I just told you that installing software is painful, maybe hard, and I just asked you to install a new software. Well, did the effort to install this container engine, then you can run basically all the software that are available in a container. So it's a good effort to do. You install just one time a container engine, and then you can run all the container that you want. That again, enabling you to run basically all the possible software that could be put inside a container. Second constraint, they should be the same architecture, meaning that the machine that is running the container should have the same architecture of the machine that has built the container. So the concept of computer architecture, of CPU architecture, could be quite technical. Let's say that for simplicity, you can think that all the CPU from Intel and AMD can be put in the big category of called AMD64 architecture. And really, they cover, I would say, probably 80% of consumer machine and almost 95% of hardware in supercomputer, in HPC system, or in remote server. So really was not so strict constraint until a few years ago, Apple decided to put a processor belonging to the ARM architecture in the most recent product. I'm talking about the M1, M2 processor, and so on. And so for this reason, the containers that were built on Intel and AMD CPU, if you don't do some additional step, they are not compatible with this machine, and vice versa. If you build a container with your brand new Mac with a M1, M2 processor, this container cannot be run on a Intel or AMD CPU. But again, this would be the same constraint when you build a software in your Mac and you want to let it run on another machine. So the same architecture constraint works basically for all the software that are released as executable. So it's really something that is one of the pillars of how software works. It's not a failure of container. And the third constraint, the third requirement that you have is that the machine, when you want to run the container, should have, in terms of operating system, the same kernel, even if different version, but the same kernel that is present inside the operating system of the container. Meaning that if you put a Linux distribution inside the container, this can be run only on Linux machine. If you put some Windows inside the container, this can be run only on some Windows system. So again, why this is typically not a constraint? Well, because in modern bioinformatics, Linux distributions are the standard distribution that people use. And even if your local machine, you have Windows, each time you want to run a software in a remote server or in a remote high-performance computing system, there, for sure, will be a Linux distribution. So sooner or later, you need to work with a Linux distribution. And for this reason, really, typically this is a constraint of using container, but in practical scenario, all the people that work in bioinformatics, at least the one that have some more experience or that need to run their application on remote server, will work with Linux distribution. So for which of you that use Docker, that is a container engine, you may say that, well, I'm able to run a Docker container with Linux in my Windows machine. Well, this is because Docker is hiding a virtualization layer that is basically emulating a Linux system to let you run a Docker Linux container inside your Windows. So the same kernel constraint is still there, even when you use Docker. Just Docker had an intermediate layer where it is virtualizing the operating system, adding some overhead to computation. And that's why it seems that in Docker, you don't have the same kernel constraint, but it's still there. It's just hidden, and they put some sugar for the final user that it seems that this constraint is not there, but it's still there. So how it works in practice, a container? Well, here there are some differences depending on which container engine you use, Docker or Singularity, as reported here in the slide. But in general, it is that a container is just an application running on your machine, like Word, like Firefox, like Chrome, okay? It's just an application running on your machine. And it's using a specific properties of modern operating system, especially Linux-based operating system. The fact that in a machine running a Linux distribution, the application are running over the operating system that is obviously running over the app. Well, Linux operating system can be split in two parts. The Linux kernel, that is the core part of any Linux distribution, the one that takes care of talking with the hardware to handle the file system and all these low-level features. And then there is, on the top of the Linux kernel, another layer that is operating system specific. The not kernel part of a Linux distribution is what makes CentOS different from Fedora, different from Ubuntu, different from Debian. All of them have a Linux kernel. They are just different in terms of the upper layer, the not kernel part. Again, what makes a Linux distribution different from the other. And each time you install a Linux distribution, you install the two things together. So here, when you install the CentOS operating system, you're installing both the Linux kernel and the not kernel part that are specific of CentOS. Well, the idea of container is making everything is on the top of the kernel as swappable component. What I mean? I mean that when you run a container, you are just running a software, a process in your machine where there is the non-kernel part of a Linux system. For example, here in this container, the creator of this container decided to put Debian, plus all the application, the library, the data that are needed to run the computation that the creator of this container decided to put inside the container. Again, the idea is that in a container, we have data, software, and dependencies, plus the not kernel part of a Linux distribution. And now you can even realize why there is this same kernel constraint. Because in a container, you just put the not kernel part, because the container is assuming that the kernel is present in the machine when the container will be run. For this reason, again, there is the same kernel constraint. But from the software point of view, the container engine will just handle the container as any other process, like, again, Firefox, Chrome, or a video game. It's just a process running on your machine. And this is telling you that you can have even more than one container running on your Linux machine. And each of these containers could be different. They could have different applications, different libraries, different data inside each container. And even the not kernel part that you can put inside each container could be different. Again, the only constraint is that we are all, in this case, Linux distribution, because they all assume that a Linux kernel is present in their machine when we are going to run the container. So, given this general idea, again, the syntax of how to use a specific container engine, how you can create a container and run it, will be covered in the second part of this webinar. Here, I would like to give you some general introduction to software containerization, to use container, including some terminology and some general workflow that you need to know each time you work with a container. So the first concept we need to understand is the concept of definition file, which is just a text file that contains the command with a specific syntax to describe what we want to put inside the container. It's like the receipt of our container. It lists what software we want to put, which data we want to put inside, which library, which dependencies, which part of the operating system we want to put inside the container. Then, thanks to the build operation that can be triggered with a command, you can convert the receipt of what you want to put inside the container in the true output, which is the container image. It is typically an immutable file that contains the computing environment for which you provide the description in the definition file. So here, inside the container image, really there are all the libraries, all the application already installed and just ready to be used. How? Well, with the run operation, when you can think about the image as an executable that contains all the application that you need and that you previously put inside the container image. And when you run a container image, well, this is formally what a container is. A container, formally, is the runtime instantiation of an image. Typically, if you are a developer of software, so you want to put your software in a container such that other users can use it, well, the knowledge that you need to have is to know the syntax, the language, how to write the receipt, how to write the definition file, and then how to do the build operation. So to be able to have an image that can then release to your colleagues, to the research community. On the other hand, if you are typically a user of software, a user of bioinformatics pipeline, for example, then the knowledge that you need to have is starting from an image, be able how to run it, maybe in different way, maybe with some advanced command. However, don't be scared, because in the second part of this webinar, you are going to learn how to write a definition file, how to build an image, and starting from an image, how to run it, having your container running your machine. So we are going to cover the full pipeline, the full workflow of working with container. Let's make a practical example. Let's say that after the second part, you know now the syntax and how to build a container. Let's say that we want to create a container that handle our bioinformatics pipeline. This is just a mix of Python and R script plus some test data. Maybe the software that we develop in the Python and R script have some requirements, as in typical scenario. Maybe we need Python version 3.7 or newer. We need R version 4.0 or newer, and we need the famous HR package to do differential gene expression analysis. And the machine, when we test and we develop this bioinformatics pipeline, is running on operating system Debian 11. Then what we can do? Well, we can create a container where we first put inside Debian 11, so the same operating system that we are familiar, where we did all the development and the test. When we put a compatible version of Python, I don't know, Python 3.9, whatever, something that fulfills the requirements, a version of R, again, that fulfills the requirements, we install the jar package inside the container, and we also put in the folder My Software, inside the container, the bunch of Python and R script that constitute our pipeline. Well, you will be able to do this after the second part of the tutorial, and you will realize that such container image, which is just a file that you can give to all your colleagues, you can put on a website, you can release to the research community, is just a file of more or less 400 megabytes, where inside there are Debian 11, a version of Python, a version of R, a specific R package, plus your Python and R script in just 400 megabytes. And when you give this 400 megabyte file to your colleagues, or when you run in the department cluster, if the three requirements are fulfilled, so there is a container engine, the architecture is the same, so maybe you have an Intel or AMD CPU, and there is the same kernel constraints, so you're running on a Linux machine, well, all the users that are taking this 400 megabyte file will be able to run your application made of Python and R script, and we will find already installed and ready to be used Debian 11, a version of Python, a version of R, the jar package, and all your script in the My folder, in the My Software folder. So, in a practical way, it means that if you go to your colleagues and ask to him or her, please, can you tell me which version of your operating system you have? So maybe he type or she type this command here in the Linux terminal, and he or she realized that he has Ubuntu 16 installed. Then you also ask to check which version of R and Python. And with these two commands here, you can recognize the two commands that you will type on the Linux terminal to understand which version of R and Python is installed. Here in the example, 3.6 and 3.5. And then you ask to your colleagues, can you please go to the My Software folder and see if you see something inside it? Your colleagues go there and they say that, well, nothing is present. Now you give to your colleagues a file that is the container, and you ask to him or her, can you please run the container and then do the same command, do the same check that I asked you before. So your colleagues with this line of code here is running the container that you give to him or her, and then ask to him or her to just type the same command. So type the same command that he used before to check the operating system. Now, here the magic appears. It seems now that when on your colleagues the container is running, Debian 11 is present. The version of R and Python are the one that you put inside the container. So R maybe version 4.2 and Python 3.9. And if now he or she go in the My Software folder, he will find the example data plus all your R and Python script. Why? Well, because here you let your colleagues run your container on his or her machine. And now the computing environment that is present on your colleague's PC is the one that you put inside the container. So Debian 11, different version of R and Python, and a specific folder where you put your script. All because you give to your colleagues the container and let him or her run it, okay? This is really the power of a container. You just give a file to your colleagues, and your colleagues find a completely new execution environment with the things that you decide to put inside the container. So I hope that you are understanding the potential and the importance of using container in science and in general in research. because really is a way for the user point of view to solve most of the issue in terms of portability, because really you have very few compatibility constraints. Once you're able to install a container engine and you fulfill the two requirements, you are able to run any software you may find inside a container. If you are a developer of software, well, this avoids you to develop different versions or release multiple versions of your software, each one that is tuned or targeted to make compatible with a different operating system or whatever. You just release one version, put inside the container, and then you know that all the world can run that container. In terms of usability, from a user point of view, is a way to have the easiest way possible to install and run the software, because really you only need to run because the software is already installed within the container. And from the developer point of view, is a way to increase the audience of your software, because all the people that are not very skilled, or if your software is hard to install, well, your audience don't need to install the software. They can just run it because you release the container. In terms of reproducibility, well, from the container user point of view, is the easiest way possible to reproduce the computational results of a study, because you just provide the same execution environment that the author of that specific study used to produce the results. And also it's a lot easier to build over that result, because you can just start from an existing container, the one that you find on that article, and just add maybe your library, your software, starting on the same building blocks that they use on the same container that they use to publish the results. And if you are, again, a developer of a container, well, is the easiest way possible to ensure the reproducibility of your results. So when the reviewer is asking you to release the code or to release the data, it's always good to release the source code and the data, but also if you release a container, really is the most straightforward way to let your results be fully reproducible. So the take-home message is, we already know that in bioinformatics it's quite common to release as open source our code, our software to release the data. Please start considering also to release a container image, because we'll have all these pros, all these good things, both from the user point of view and from the developer point of view. When we talk about container, more formally, we are talking about one of the possible virtualization strategies. So container is not the only way to virtualize an environment, to virtualize some software. Container is one of the most famous way to implement a mechanism that is called operating system level virtualization. But there is another class of virtualization called full or hardware level virtualization, where the most famous example are virtual machine. So virtual machine or VM are some sort of, if you want, competitor of container. They are achieving a similar goal, but in a different way. What virtual machine did? Well, in a virtual machine, you are emulating an entire computing system, like this emulator for video game that you find on the web. So you are emulating the hardware, you are emulating a virtual CPU, a virtual RAM, a virtual disk, and so on. Plus, you are putting an entire operating system inside the virtual machine. And on the top of this, you install inside the virtual machine the software, the libraries, the data that you want. They are very used in academia, in research, in industry. I guess that if you are a student, you have the chance to use during your study some virtual machine, maybe in some laboratory. They are very important for modern cloud computing. Really, they are the building blocks of modern cloud computing. And also, they don't have the same kernel constraint, meaning that I can put in a virtual machine Ubuntu or any Linux distribution and run this virtual machine maybe in a Windows system. Like reported here in this picture, you recognize that the hosting operating system is Windows, and here I'm running a virtual machine with inside some version of Ubuntu. So all these things may seem some good things. So why we are talking this webinar about container and not about virtual machine? They are very famous, very used. They have no same kernel constraint. Why using container instead of virtual machine? Well, it's all a matter of performance. Indeed, when you run a container on your machine, it's like running a process where inside the process there are directly the application that you want to run. The container is just a process running on your operating system that is on the top of your hardware. Here, the hardware could be, again, your laptop, your workstation, your department cluster. On the other hand, when you run a virtual machine, where maybe here, in terms of application, you put the same one that you would like to put in a container, then inside the virtual machine, there are the software that you want, but there is an entire new operating system, plus you pay the overhead to emulate CPU, RAM, and disks. So this distance here from the application you want to run and the hardware is really all overhead that you pay in terms of performance to be able to run your application, an overhead that you don't have when you use container. So virtual machine and container achieve a similar goal, but they did in a completely different way. So in terms of efficiency, containers are a lot more efficient. They don't need to run an entire new operating system in addition to the one that is already present in the machine, and we don't need to spend CPU time in virtualizing some hardware. So they use less resources and they are more efficient. To start or to stop a container is a matter of nanosecond or millisecond, while if you use virtual machine, you know that depending on the hardware, it may take some seconds or minutes. Then just releasing a container image is a file of some hundred of megabytes or a few gigabytes, while when we want to release a virtual machine, they are typically dozens of gigabytes. Something that have even an impact on how easy it is to deploy, to move, to put on a website. The lower is the size of a file, the easy is to share it. However, there are even some pros, as we saw before, in using virtual machine. For example, you have no more the same kernel constraint. The operating system that you can put here may be different from the operating system that you put here. Maybe here you have Ubuntu and here Windows, or vice versa. In terms of the CPU architecture, the constraint is still there. So if you have a virtual machine built on an Intel CPU, it can run on an Intel or in an AMD CPU, not in an ARM CPU. So the same constraint that you have with container. So for this reason, they achieve a similar goal, but the efficiency on how they did it is a lot different, and containers are a lot more efficient. Another alternative to container, just to be fair and complete, are virtual environment, and one of the most famous, Conda, that is both a virtual environment and a package manager. So for which of you that are not familiar, virtual environment are cross-platform, lightweighted, self-contained Python installation that are just easy to set up and just to run. Basically, in a virtual environment, you put the application that you want, and then you are able to export the virtual environment to give this to your colleagues, and you're just basically exporting the receipt on how it can be rebuilt, this virtual environment, on another machine. One of very famous virtual environment that again have also a very large software repository, is a very famous package manager, is Conda. It is an open source, cross-platform, and language agnostic package manager and virtual environment manager. Conda, as you may experience if you are a Python user, is used a lot. It has a lot of pros. It has a huge library of software that you can install with a few commands. The Python environment you create can be, again, exported. You can give this Python environment to your colleagues, such that is able to recreate this environment, reproduce your computing environment. It can be installed without the root permission. But there are some limitations, even in this nice piece of software that is Conda. For example, in Conda, when you export your environment, first of all, you're exporting the receipt on how to rebuild. So you're not exporting a file, an environment is ready to be run by your colleagues. You are exporting the receipt that your colleagues can use to recreate automatically, but recreate the environment. And in this environment, you put some file or you install some custom software. Well, these are two elements that cannot be exported, and so that your colleagues is not able to have. Also, it is possible through some command to alter, to change the Conda environment. So that property of containers that are immutable, and for this reason, they ensure reproducibility, here is broken by Conda, because your colleagues that receive your environment can alter it. And so, by definition, his environment, her environment, can do something different from your environment. So to have a table that tries to recap, container and virtual environment, or specifically Conda, they are all very efficient. They all use very few resources, and they are very fast to start and stop. Even in the size where a container image are some hundred of megabytes or gigabytes or few gigabytes, while an environment, well, typically you share the receipt on how to build the environment. So it's a text file, few megabytes. In terms of the same kernel and the same CPU architecture, two constraints that we have with container, well, they are still present in virtual environment Conda. Even here, the thing is a little bit more subtle, because still, if you are using a Conda environment or a virtual environment that is relying on some library that are present only on some operating system, or that are present only for some CPU architecture, still, when you export the environment and you give to your colleagues will not be able to install that library, that software. So there is no same OS constraint and no same CPU architecture constraint, only if a software you use is available on all the operating system and on all the CPU architecture. If it's not true, still you have the same OS constraint and the same CPU constraint. It depends on the software. This is the take-home message. In terms of installation, really, when you are sharing a container image, you are sharing already the execution environment set up and ready to be run. When you share a virtual environment or a Conda environment, you are sharing the receipt that then your colleagues can use to recreate the environment. So here you are sharing the environment, here you are sharing the receipt on how to create again the environment. What you can think to put inside and then be exported, well, in a container, anything that you can think to be put inside can be put and can be exported. File, folder, environmental variable, libraries, package, whatever. On the other hand, on virtual environment or in Conda, you cannot export any file that you put inside in the environment, or any custom software that you put inside the environment. Only the packages and the dependencies in Python that are present in the Conda repository can be exported. So there are these other limitations. So just to give you an idea of why in this webinar we talk about container and we don't talk about virtual machine or virtual environment or Conda, because container has all these pros compared to virtual machine and virtual environment that make them quite useful and very used in bioinformatics. So now that I hope that I convinced that containers are a good option to encapsulate your software in a way that is portable, reusable, and reproducible, well, which container engine there are out there? How I can use in a practical way a container? Again, you need to install a container engine. And there are many container engines out there. The most famous is for sure Docker. In this webinar, we're going to learn how to use Singularity or Uptainer. There are many, many of them. Each of them has some different characteristics and some pros and cons that make it more suitable for a specific application or for a specific environment. The idea is that each time you want to choose a container engine, you should choose a container engine that is well supported, well documented, and that have a large adoption in your field. So maybe in bioinformatics, there is a container engine that is more used compared to, I don't know, astrophysics. So maybe depending on the field, you may find more useful a container engine compared to another. Then you should also check if the container engine is able to use properly advanced hardware, or if it can be run smoothly in a remote server. And also, very important, check if the container engine have a large base of users that can provide already built and existing container image. So container repository is a very powerful resource, huge catalog of container images done with a specific container engine that the user can find on the web and maybe just use it. So this is another criteria on how to choose a container engine. If you add an additional requirement to the choice of a container engine, that is, it should be suitable to be run in a remote server, in your department cluster, in an HPC system, meaning in a system where you have a research manager or a scheduler like Slurm, when you want to run advanced parallel software, when you want to have very high efficiency, when the machine that you're going to use is shared by many users, maybe even by many departments, when there are some specific and advanced hardware like GPU, and you want, since this machine is a remote machine, you are not the administrator, you want to be able to run your container not as the administrator, so technically rootless, well, that huge list of container engine shrink a lot, and there are just three main options for container engine in HPC environment that are Singularity, Charlie Cloud, and Shifter. So for this reason, even if Docker is the most famous, is the most adopted software, is a mature software, well documented, well supported, is used a lot in industry and research, and is a huge catalog of already built image. In this tutorial, we are going to learn Singularity, because Docker is not the best option when you want to run software in a remote server, in a HPC system, a very common scenario in bioinformatics where the size of the data is such big that it cannot be handled by your workstation or by your laptop. Indeed, Docker, it has a lot of pros, but is not efficient as Singularity. You need to have root privileges to run the containers. You need to be the administrator of a machine to run the container, something that you cannot have in a remote server, and it does not have a good integration with scheduler such as Singularity. On the other hand, Singularity is the de facto standard container engine when you want to run on remote high-performance computing system. It is even as Docker, well supported, well documented, is increasing its popularity a lot. And very important, in Singularity, you can use all the containers that you build in Docker. So all this huge catalog of container or even any other container that you can build in Docker, it can be used in Singularity. And to do this, Docker should not even be installed in your system. It's Singularity that is taking care of translating a Docker container in a Singularity container. So for all these good features, Singularity is the de facto standard to run very high demanding software in remote machine, and is the container engine that we are going to learn how to use in the second part of this webinar. So I conclude this overview of what it means using container and software containerization. If you have any question about this or any other webinar, here there is the link to the Google Docs when you can put your question, and also the link we will put in the description of the YouTube video here in the channel. And now I think that we can have a 5 minutes break, and we can continue in 5 minutes with the second part when we are going to learn how to use Singularity, so a software that allows us to create in practice a container and run a container. Thank you.
Okay, so welcome back, everyone. So let's start with the second part of this webinar. I'm Giulia, and I will present the container image that we'll learn today, which is singularity. So first, I will introduce you what is singularity, the main characteristics, and the general workflow. And then we will learn how to work with the Singularity engine. So how to run an image, how to build an image, and how to write a definition file. So first of all, Singularity is a free and open source container engine that is target specifically the remote server and works for Linux-based operation system. Originally was developed at the Lawrence Berkeley National Laboratory, but now it's at the company's C Labs. There is also a commercial version of Singularity, which is the Singularity Pro. So here there is some website where you can learn about Singularity, and also a guide to learn how to install Singularity. As some of you already know about Obtainer, so Singularity is now under the Linux Foundation. So they renamed Singularity as Obtainer. But in this webinar, we use these terms as synonyms, so Singularity C, Obtainer, and Singularity. Since the branch are in line, this means that they have roughly the same features. So here we use just as a synonymous term. So as Giacomo presented before, this is the general workflow of a Singularity container. Just to recap, we need to know three information. The first one is the Singularity definition file, is the first element we need to know, which is the text file that contain the Singularity commands to create the image. So the receipt on how to create our container. So the software we want to install, the data we want to include, and so on. With the build operation, we create an image, which is a file with extension SIF that contain the computing environment. So the libraries, the application, the software, and the data that you declare to put in the definition file are there. And then from the image file, you can run the container. So it's like having an application where inside you have the library and software and so on containing in an image. And here you can run any commands. So usually if you are a developer, you need to know how to build an image starting from the definition file and creating the zip file. Instead, usually, if you are a user of the containerization, usually you need to know how to run an image. So run a container. Let's start from the Singularity image. So as I said before, is a file with extension SIF, which means Singularity image format, and it's immutable. What does it mean? This means that we can only use what is inside the image. You cannot modify that. So, for example, you can use the software and libraries that are contained in the container. However, you cannot alter, you cannot update the package. You cannot delete or modify the files that are present in the container. You can only use what is inside the container. This is the definition of immutable. Of course, there is also the possibility to cryptographically sign or encrypt the zip file. So today we will see these three different scenarios that have an increasing complexity. So starting the first one, especially when you're a user, someone provide you the image file, so the zip file, and you need to run the container. The second scenario is that, for example, you need to build a container or from a pre-built image that is present in the internet, or some of your colleagues, for example, provide you already the definition file. And with the build command, you create the image, and then, of course, you can run the container. The last one, which is the most challenging one, is usually for developers. So we want to create our own image. So starting from define the definition file, so the receipt, what we want to include in image file. Let's start from the simple one. So someone give you the CIFF file, so the image, and you want to run the container. To run the container, you need to know 3 different commands. The first one is the exec commands, which allow you to execute any commands within the container. So in this case, you can use the software, library, dependencies, data that are present within the container. Let's make an example. For example, I have my C file that someone provided, my cont.cif, and I have in my PC this hello world API, this script that I want to run inside the container. So this is the syntax: singularity exec, the name of the image file, and then the command I want to run, that in this case, of course, is Python 3, and the Python script I want to run, hello world API. So how it works? We have our PI script in my system. I have my image file in the system, and I want to run this script inside the container. Of course, this file is visible inside the container, and we will see in the next slide how it is possible. And in this case, this script is executed within the container, so using the Python version installed within a container. Even if in your computer Python is not installed, you are able to run this script. And then the output will be provided in the host shell. To follow the example provided by Giacomo, so we are in our computer with Fedora 34, this version of Python, MATLAB, and of course Singularity. In our PC, we have some folder and files. So here we have our 2 files, so the image file, my cont.cif, and the script I want to run, hello world API. What is inside the image? In the image there is Ubuntu 20 with R version and Python version 3.6. As you can see, it's different from my version in my computer. And then inside the container, there will be other data. What happens when I run the container inside my computer? So what we obtain is that I can run this script, hello world API, with the Python version that is present in the container. But how it is possible that the container is able to see my data? This is because by default, Singularity links some folder by default, some folder that are present in your host system, and will link directly in the container. These folders are the user home directory, the temporary directory, and other system directory. This means that inside the containers, these directories are visible, so you can read and write in this folder. For example, in this case, when you run the container in your PC, these 2 folders, so the home directory and the temporary directory, are visible inside the container. And this is true also for the files that are present in the folders. So in this case, hello world API is visible inside the container because it's present in the home directory that is by default linked in the container. But what about if I, for example, wanted to make available also other folders which are not the default one? Well, there is the possibility to do this, which using the --bind options. So, for example, think about of that hello world PI requires some text file as input. That is example, for example, example txt that is available in my host directory data input. So I can map this folder inside a container using the ---- bind options. So now the syntax is singularity exec is not changed. And then we have the option ---- bind, the folder, the host directory that I want to map. So in this case, data input, and then the folder that will be present in the container where to link this folder. And in this case, I will call mount. Of course, you can use other name for this folder. So this means that now what is present in the data input will be present in the container inside the mount folder. And then, of course, there is the image file and the command you want to run, which is Python hello world PI, and the file provided as argument. As you can see, the path to the txt file is not the one of the host directory. It's not the one present in my PC. It's the one present, is the container folder present in the container. So to follow in this example, so in red we have the default folders that are bind by default by singularity. So the home directory and temporary directory. With this line, so with this option, we're able to bind also another folder, which is the data input, and in the container will be named as mount. And inside the mount folder, there will be all the files that are present in data input. This is, again, to stress this fact. So if you want to run this hello world PI in your PC, the command that you have to run in the terminal is python free hello world, and the path, the relative path in your PC in the txt file, so data input. But within the container, this folder does not exist, is not visible. What is present in the container is the mount, so the link, in this case, to the data input. So the path that we use is not the one of your host PC, but is the one in the container. So in this case, mount. So if you run this with the data input, so the host folder, in this case, it will not work and provide an error. So we have seen the singularity exec command. So again, this is the syntax. So singularity exec, some option, the image file, and the command you want to run. Of course, if you want to bind other packages, other folder, for example, you have to include in the option ---- bind with the host directory, followed by the container directory. The second command you need to know is the shell command, which allow you to spawn a shell within the container and to interact with it, but just running some command inside the container interactively. The syntax is similar to the previous one, so we have singularity, shell, and the cif.if file. So in this case, the name is ubuntu.cif.if. This open a shell inside the container when you can type, we can run the command. For example, here was just checking which is the operating system that is present inside the container. And in this case, for example, is Ubuntu. And then you can exit from the shell, from the interactivity using exit. Again, you can use also the flag ---- bind. The shell command is very useful, especially when you have to debug and to test the container. So you may use it to check if some libraries or the version of the libraries that install and so on. The third command is run. we will see that in container may contain the so-called run script, so a script that are automatically executed when the container is starting using the specific command run. So this is the syntax, so singularity run and the image file. What is the run script? So are a set of commands that are included inside container and that are invoked every time you start the container using the run command. This is particularly useful when, for example, your container provides some pipelines or an operation that is the same, but you need to provide, for example, change only the input file. So, for example, in this case, let's consider this image file that have as a run script this function that count the number of lines in a text file that are passed as input parameter. So in this case, the syntax is singularity run, the image file, so the CIF, and as input parameter my.txt. So in this case, provide as output in the shell the output of the command. So in this case, it's not the user that specify the command, but the command is already plugged in inside the container. To sum up, so we have seen 3 different commands. We have the singularity exec, which allow you to execute almost any command inside the container, a command that you can choose with this syntax, so singularity exec, some option, the image, so CIF file, and the command you want to run, the singularity shell to spawn a shell inside the container, so singularity shell, some option, and the image file, and finally the singularity run, so execute the run script that is present in the container with singularity run, some options, and the image file. Just remember what I said before, and also Giacomo stressed this idea, is that the image is immutable. What does it mean? Let's, for example, open interactively this image, so with singularity shell. And here I can check the operating system, I can check the R version, the Python version, then I try to update or install other package. We got an error. Why? Because the container is immutable. This means that I can use what is inside the container. I can change that. I can update the software and can install new software. I cannot add or remove file. It's immutable. So I can just use what is inside the container. Here there is other flags that might be useful for the exec shell run. We have seen bind, but there is also PWD, which is allowed to set the starting directory of your container. So for, when you start a container, it did start from the current folder. When you were running the container, you can set also another directory and allow you to pass environment variables. No home allowed you to not bind the user home directory if you don't want, enable CPU computing, and also enable that the file system is accessible as both write and read mode. Okay, so we have seen how to run a container starting from the image file. Now, for example, we want to download from the internet a pre-built image, or some of your colleagues, for example, provide you the definition file, so receipt to build the image. So we will see the build command to create the CIF file that can be run with the command we have seen before. So also, as Giacomo said before, there is online some repository of images. For example, the Singularity library is the one of Singularity that allows to download existing pre-built image, or also you can upload your own image. In the Singularity libraries, there is both base images, so images that contains, for example, only the operating system. Others that provide also already some application. So to download and build the image starting from the image providing Singularity library, this is the syntax. Sudo singularity build, the name of the image we want to create. So for example, .cif, and then library, followed by the remote path that is present in Singularity library. The same can be done for the Docker Hub, so the other repository that contains the Docker image. So the build commands allow to download the Docker image and convert it to Singularity image. Again, the syntax is sudo singularity build, the name of the image, and then Docker followed by the path, the remote path present in the Docker Hub website. However, the build command can be used also to build the image starting from a Singularity definition file. So this is, again, the syntax, sudo singularity build, the image file we want to create starting from the definition file. For example, if we want to build the image, myimage.cif using the definition file that someone provided to me, which is my def file with extension ef. In this case, the syntax is sudo singularity build, my image cfi, and my def file .def. So the build command, again, can be used to download an image from the Singularity library, to download an image from Docker Hub, but also to build an image starting from a Singularity definition file. I don't know if someone you have already noticed, but what is changed with respect to the run exec and shell command is here the sudo before Singularity. This means that both commands requires the root privilege. So this means that, of course, if you want to build an image, you need a Linux operating system because Singularity works only on a Linux system. You need, of course, Singularity installed, and you need to have the root privileges, which is not true always. Maybe true for your PC, but for example, not in any server, you have the root privilege. So in that case, you can only run the container. You cannot build the container. This, of course, will not be true for the BioHackathon when they will provide you a system with root privileges, so you will be able to bind. But in general, if you need to bind to build an image, you need to have a root privileges. There is also some alternatives. For example, you can use the remote build option that allows you to send a definition file they build in a Linux-based machine remotely, or a recent version of Singularity support also the rootless build, where you can check, for example, the option -- fake root if you want to learn more. So we have seen also how to build the image starting from definition file or from the internet. Now, instead, let's move to the most difficult one, which is usually for developers. So how to write your own image. So developing the definition file, so the receipt of what we want in the image, in the container. So a Singularity definition file is a text file that contains, as I said before, the receipt on how to build the container. So the library, the software, the data you want included in the image. In particular, it has two main sections. The header that is described, which is the base image, the operating system, and the existing image when you want to start. The body instead describes which are the libraries that we want to include inside the package, so the software, the data, libraries, together with additional configuration. This is the most important area when you develop a container, and the idea is that if you're able to install and configure the software that you want, that you need to run your application in your PC using a Linux terminal, then you should be able to install it in a container. Why? Because the exact same command you will use to install the library software in your PC will be put in the definition file. So in the definition file, it's like having a scratch PC where you have to install the software that you need. And this is the key idea to develop containers. So for example, we want to develop a container with the operating system Debian 10 and some libraries like Python, R, and some software from Git repository. With few lines here, we are able to build the container, to create the container. As you can see, there is a header and a body section. In the header, we will see later the keywords that we use, but here we are saying that we want to start from an image that is available in the Singularity library. And the image that we want is the one with the operating system Debian 10. Here instead, in this section, we install the package that we need. And as you can see, it's the exact same command you would run in your Linux terminal to install the packages. So you want to install R, you want to install Python, you want to install Git, you want to create a folder, you can move to the folder, and then you can clone the Git repository. So it's the same command that you would run in your PC to install these software and libraries. So going into details about the definition file, starting from the header. So the header is the first part of the Singularity definition file. It has the first keyword is bootstrap that allows you to indicate from which base image you want to start. So usually you start from a base image and then you install, you build, you put other data, software, libraries, and so on. There is different keywords you can use, different, you can download and use different base image. For example, using library, you are using the image that is present in the Singularity image repository. If you're using Docker, for example, you are starting from image from Docker Hub, C-Hub from other Singularity image repository. You can also start from an image that is present in your file system, so a local image. So these are examples to understand more what I'm talking about. So for example, if I want to start from an base image from the Singularity library, the first line will be bootstrap library. If I wanted to start from a base image from Docker Hub, will be bootstrap Docker. If we want to start from a local image, will be bootstrap local image. The second line instead indicate which are the base image you want to start. So for example, here we want to start from Debian 10 that is present in Singularity library. Here we want to start from the image that is present in the Docker Hub with CUDA. Here instead, we want to start from this image file that is present in your local system in the documents folder inside your home directory. Let's move to the body. So the main part of the Singularity definition file defines what the container, how the container is built, and what will be inside the container. The body section contains several subsections that some of them, of course, are optional. For example, there is the file section where you want to, when you want to copy some file inside a container. Environment that allow you to set and define environment variables. Post where, as you've seen before, you want to install the software libraries, create the directory file, download file to internet, and so on. The run script is the one that I was talking before, is the commands that will execute automatically when you run the container using the Singularity run. Labels to add some metadata and help to provide additional information about the container you were developing. So containerization details, file section allowed to copy some files that are present in your PC inside the container. So this is the syntax. So we have the source and destination. So the source is the path to the file inside your PC. So for example, in this case, I want to copy the model parameter file that is present in documents folder inside my home directory. And I want to put this file inside the container, inside the path, the folder mount. If you don't put the destination here, so by default, this file, in this case, not.txt, will be copied inside the container with the same name and with the same path. So in this case, in the home directory documents. This is similar to the binding option, but in this case, we are copying the file inside the container. This means that if you share the image to your colleagues, also your colleagues will have inside the container these files. The environment section allows to define which are the environmental variables. Be careful because these will be set at running time. So will be used during a running time. If you need during the build time, in this case, must be specified in the post section. So the post section is the one that we have seen before, that is where I install the software libraries and that I need inside the containers. So for example, in this case, I can install Git, I can create new directory, move to directory, clone a repository, install other packages, and so on, and also setting environmental variables. The run script is the section where you specify the commands that the container will invoke when you use the Singularity run. So it's the default behavior of the container. Finally, the labels allow you to add some metadata. For example, the author of the definition files and the version of the definition file. And the help section allows you to specify information about the container that can be accessible using Singularity run help. So this is an example, a more complete example of a definition file. The body of the definition file. So in this case, I'm copying this file inside the container in the mount folder. I'm setting some environmental variables. Here I'm updating the libraries and I'm installing GCC and Git. I'm creating a new directory and moving to that directory and cloning the data, setting environmental variables, and so on. In the Rust script, I instead put the default command that should be run when you use a Singularity run, the author James version 1.0, and the help that described what the definition file contains. Finally, this is the last slide that is the most important one because allow you to understand what gives you the full reproducibility of the container. So the full reproducibility is guaranteed not by the definition file, but by the container image. So what we want to share with other people is not the definition file, is not the receipt of the container, but is the CIF file, so the image file. Why? Because if we provide, for example, this definition file, where, for example, it was starting from Debian 10, was copying some folder, install some packages, what happens if you build the image few months later or year later, you will not obtain probably the same image. Why? Because Debian 10 image in Docker Hub is regularly updated. So for example, here the default one might be Debian 10.1, but I don't know, next year will be Debian 10.10, for example, or 5 and so on. when you copy the file, so for example, I was copying this file inside a container, even if I build in the same container that I used to, but maybe this file is changed over time. Now, of course, will be different. So the file that will copy inside the container will be different. Or for example, let's install some package like Git. Of course, also Git is updated. So if I install today and then I install a few months later, will not be the same Git. It's not the default Git. And also the repository. If I install now this the clone this repository, will probably be different by cloning the same repository few months later, years later, because it will be updated. So this is the most important things you have to take home message is that the reproducibility is guaranteed by the image and not by the definition file. So thank you, of course, for the attention. I hope to be clear. If you have any question, you can write live in the comments. Or, if, for example, we provide you the form where you can submit any question. And in a final webinar, the question action session, will be a section where we answer to all your questions. Thank you.
Okay, so thank you again to all the people that attend this webinar. As always, the video will be also recorded on the YouTube channel. Also, let me say thanks to Salvatore, that is the man behind the scene that is taking care of, all the direction, moving people, coordinating this live, create the links. So big shout out to Salvatore that take care of all the technical stuff. Without all the technical stuff, this webinar will be not possible. So thank you, Salvatore, for taking care. Thank you to all the speakers, to Giulia and Luca, to you for your attention. And again, we point out to the next webinar that will be in a few weeks, that will be about single cell RNA sequencing, especially the part of the wet lab, the part of the processing of the data. So now that we know how to use the remote system, the HPC provided by University of Turin, and how we can containerize our bioinformatics pipeline, we are going to learn in next webinar, how the data that we are going to handle, single cell RNA sequencing data, how it's built, what are the characteristics of this data, and how we can do some basic preprocessing. But I would say that is everything for this session. So thank you again, Luca, Giulia, and Salvatore for this first webinar. And we are going to see in a few weeks. Bye. Thank you.
Bye. Thank you.
Thank you.